Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon and welcome. My name is Kirsten Wiley, and I'm here today to introduce and welcome Richard Panik, who is visiting us as part of the Microsoft Research Visiting Speaker Series. Richard is here today to discuss his book, The 4% Universe, Dark Matter, Dark Energy, and the Race to Discover the Rest of Reality. It's hard to imagine that what we can see, touch, hear, smell, and taste is just 4% of what is actually out there. The rest of the universe is unknown, it is dark, and scientists have been working hard to determine the roles dark matter and energy play. The 4% universe traces the path of one of the most mysterious scientific concepts we know of today. Richard Panik is the recipient of a Guggenheim Fellowship and the author of The Invisible Century and Seeing and Believing. He has frequently written for the New York Times as well as Discover, Smithsonian, Esquire, and Outside. He has received a New York Foundation for the Arts Fellowship in Nonfiction Literature and has an Antarctic Artists and Writers Program grant from the National Science Foundation. Please join me in welcoming Richard Panik to Microsoft. Thank you.
Thank you. Thanks for coming out. It's a great turnout. I appreciate it. Thank you to Microsoft for inviting me, and thank you, Kristen, for that introduction. Over the weekend, I was signing books at one of the Air and Space Museums in Washington, and there was a table, and I was sitting there signing books, and there was a cashier there, and the cashier, was just flipping through the book, and she read the inside flap, and she went, "Wow, that's crazy!" And I thought that's the perfect response. It's great. It was very gratifying because it is crazy. And I know that sounds like a made-up anecdote, but it's actually true. And as soon as it happened, I thought, oh, I can use that in talks. So what I'd like to do is put this, this is truly a revolutionary concept in science. And you hear those words a lot, and I was very glad to see that one of the early reviews said, this is a media cliche, but in this case it's not. This is from scientists' points of view. From the scientific community, this is really revolutionary, and it's something that that the public and probably, well, who here has heard of dark matter, dark energy, those ideas? Yeah, so most people have, but the enormity of the concept and what it's going to mean hasn't really penetrated, and that was actually part of why I wanted to write this book. I thought about it a lot, I researched it a lot, and like that, the cashier I was talking about my first response was something like, wow, that's crazy, or that's wild, or that's too wild to be true. This was about 10 years ago when I first started hearing about it, when I would go to conferences as part of my research. But then the more I looked at it, the more I realized that it wasn't hyperbole, it wasn't just some PR thing, but that it was actually the scientists themselves were taking it seriously, the astronomers and the theorists, the cosmologists, the physicists. And as I saw them taking it seriously and trying to knock down these ideas and failing and convincing themselves, I became more convinced until I thought, well, this is a story worth telling. How they reached that point, so this is a very human story in terms of people really working through these problems. So what I'd like to do, I know that these things aren't usually readings, and I'm not going to read much, but I think to set up what I'm going to talk about, I would like to read the prologue, which is only 3 pages long, and it'll take about 5 minutes. So if that's all right, I'll do that, and then I'll kind of walk through the rest of the story. So this is the prologue, so you don't really need any setup, except that it's brilliant, but other than that, you just... The time had come to look inside the box. On November 5, 2009, scientists at 16 institutions around the world took their seats before their computer screens and waited for the show to begin. 2 software programs being run by 2 graduate students, one at the University of Minnesota, the other at the California Institute of Technology, simultaneously. For 15 minutes, the 2 scripts would sort through data that had been collecting far underground in a long-abandoned iron mine in northern Minnesota. Over the past year, 30 ultrasensitive detectors, deep freeze cavities, the size of refrigerators, shielded from stray cosmic rays by half a mile of bedrock, their interiors cooled almost to absolute zero, each interior harboring a heart of germanium atoms, had been looking for a particular piece of the universe. The data from that search had sped from the detectors to off-site computers, where, following the protocol of a blind analysis, it remained in a box, out of sight. Just after 9 a.m. Central Time, the unblinding party began. Jody Cooley watched on the screen in her office at Southern Methodist University. As the coordinator of data analysis for the experiment, she had made sure that researchers wrote the two scripts separately using two independent approaches so as to further ensure against bias. She had also arranged for all the collaborators on the project, physicists at Stanford, Berkeley, Brown, in Florida, Texas, Ohio, Switzerland, to be sitting at their computers at the same time. Together they would watch the evidence as it popped up on their screens, one plot per detector, two versions of each plot. After a few moments, plots began appearing. Nothing, nothing, nothing. Then, 3 or 4 minutes into the run, a detection appeared on the same plots in both programs. A dot on a graph. A dot within a narrow, desirable band. A band where all the other dots weren't falling. A few minutes later, another pair of dots on another pair of plots appeared within the same narrow band. And a few minutes later, the programs had run their course. That was it then, 2 detections. Wow, Cooley thought. Wow, as in they'd actually seen something when they had expected to get the same result as the previous peek inside a box of different data nearly 2 years earlier. Nothing. Wow, as in if you're going to get detections, 2 is a frustrating number, statistically tantalizing but not sufficient to claim a discovery. But mostly wow, as in they might have gotten the first glimpse of dark matter, a piece of our universe that until recently we hadn't even known to look for, because until recently we hadn't realized that our universe was almost entirely missing. It wouldn't be the first time that the vast majority of the universe turned out to be hidden to us. In 1610, Galileo announced to the world that by observing the heavens through a new instrument, what we would call a telescope, he had discovered that the universe consists of more than meets the eye. The 500 copies of the pamphlet announcing his results sold out immediately. When a package containing a copy arrived in Florence, a crowd quickly gathered around the recipient and demanded to hear every word. For as long as members of our species had been lying on our backs looking up at the night sky, we had assumed that what we saw was all there was. But then Galileo found mountains on the moon, satellites of Jupiter, hundreds of stars. Suddenly, we had a new universe to explore, one to which astronomers would add over the next 4 centuries new moons around other planets, new planets around our sun, hundreds of planets around other stars, 100 billion stars in our galaxy, hundreds of billions of galaxies beyond our own. By the first decade of the 21st century, however, astronomers had concluded that even this extravagant census of the universe might be as out of date as the 5-planet cosmos that Galileo inherited from the ancients. This new universe consists of only a minuscule fraction of what we had always assumed it did. The material that makes up you and me and my laptop and all those moons and planets and stars and galaxies. The rest, the overwhelming majority of the universe is, who knows, dark, cosmologists call it, in what could go down in history as the ultimate semantic surrender. This is not dark as in distant or invisible. This is not dark as in black holes or deep space. This is dark as in unknown for now and possibly forever. 23% something mysterious that they call dark matter. 73% something even more mysterious that they call dark energy, which leaves only 4% the stuff of us. As one theorist likes to say at public lectures, we're just a bit of pollution. Get rid of us and everything else we've ever thought of as the universe, and very little would change. We're completely irrelevant, he adds cheerfully. All well and good. Astronomy is full of Homo sapiens' humbling insights. But these lessons in insignificance had always been at least somewhat ameliorated by a deeper understanding of the universe. The more we could observe, the more we would know. But what about the less we could observe? What happens to our understanding of the universe then? What currently unimaginable repercussions would this limitation and our ability to overcome it or not have for our laws of physics and our philosophy, our twin frames of reference for our relationship to the universe. Astronomers are finding out. The, quote, ultimate Copernican revolution, as they often call it, is taking place right now. It's happening in underground mines, where ultrasensitive detectors wait for the ping of a hypothetical particle that might already have arrived or might never come. And it's happening in ivory towers, where coffee break conversations conjure multiverses out of espresso steam. It's happening at the South Pole, where telescopes monitor the relic radiation from the Big Bang. In Stockholm, where Nobelists have already begun to receive recognition for their encounters with the dark side. On the laptops of postdocs around the world as they observe the real-time self-annihilations of stars billions of light years distant from the comfort of a living room couch. It's happening in healthy collaborations and, the universe being the intrinsically Darwinian place it is, in career-threatening competitions. The astronomers who have found themselves leading this revolution didn't set out to do so. Like Galileo, they had no reason to expect that they would discover new phenomena. They weren't looking for dark matter. They weren't looking for dark energy. And when they found the evidence for dark matter and dark energy, they didn't believe it. But as more and better evidence accumulated, they and their peers reached a consensus that the universe we thought we knew for as long as civilization had been looking at the night sky is only a shadow of what's out there. That we have been blind to the actual universe because it consists of less than meets the eye. And that universe is our universe, one we are only beginning to explore. It's 1610 all over again. So that's the prologue, and I wanted to read it so that you would get a sense of the historical perspective, the historical setting for this discovery. That my argument in the book, and it's one that scientists would agree with, is that this is a revolution in thought and in science on a scale with the one that Galileo had in validating the Copernican interpretation of the universe. The Copernican interpretation of the universe, of course, has the sun at the center, and there's been a kind of misunderstanding over the centuries, a mythologizing that this was a blow to our ego. In fact, it wasn't. The center of the universe was seen as the bottom of the basement, the bottom of the house, the basement, where everything impure fell. So, and the celestial, the things that were outside of Earth, were beautiful and perfect. So it wasn't really a demotion to have the sun at the center. It was just counterintuitive, and it presented problems to the church, of course, and there was all sorts of, we know that history. But the lesson that we took from it in saying that we are not the center is, so it's not a blow to the ego, but it's a rethinking of the universe, that there is no privileged place in the universe. And by privilege, I don't mean special, I just mean that there is a place that is actually the center. Same thing now with this, that we're finding out that 4%, that the universe that we've always thought of is only 4% of what's actually out there in terms of the matter and the energy. And Einstein tells us that matter and energy are interchangeable, so that's really it for the universe. So there's 4% that we know of. And this other part is mysterious. So finding out that we are only what we've always thought of, what astronomers have always looked at, is only 4%, is perhaps humbling to our egos in terms of our investigative prowess, but it's not a blow in any other sense except that it's consistent. It's consistent that we are not special, that there is not this special frame of reference. Okay, so let me back up now. Excuse me. Excuse me. So let me back up now and say, where did these ideas come from? In the 1970s, starting in the late 1960s and then throughout the 1970s, astronomers were observing the motions of galaxies. They were observing the individual motions of galaxies, these spirals that circle, and they were observing the motions of how galaxies interact with other galaxies in clusters. And they were looking at computer models of our own galaxy. And what they were finding consistently is that galaxies moving at the rate that they're moving, orbiting or rotating at the rate that they're rotating, should be shredding apart according to the laws of Newton. They should be sending gas and stars in every direction. The Milky Way galaxy, our galaxy, which has gone through, I think it's a dozen rotations so far, shouldn't have survived the first rotation based on the matter that we can see. However, if you say that there's other matter there, and the computer simulations that they ran, and these were, primitive things that were done with punch cards and Fortran and, stacked in feeders that went into, huge things like this. That those computer simulations showed that if you take the galaxy, the spiral galaxy, and you put like a halo of dark matter on it, it still didn't stabilize. I mean, dark matter, whatever it is, that they didn't use the term dark matter yet, but this mystery matter, it didn't stabilize the galaxy. So they made a bigger halo, and that didn't stabilize. And they kept making bigger halos until finally the halos were like this, and the galaxy was like this. And then it stabilized. And that was tough to believe, and people fought against it, as you might expect. The observers, there was this one observer in particular who I spend a good deal of time on in the book, because she's just great, Vera Rubin. Just went out and made these observations again and again, galaxy after galaxy. You could see it, you could plot it, the rotation, what's called the rotation curve, the speed against the velocity of the rotation, and you would just see the line stay flat. The velocity versus distance, you would just see the line stay flat. It should fall off at distance in the same way that in the solar system, Pluto moves at a rate that is much slower than Mercury, which is doing this, right? But this is as if Pluto were keeping pace with Mercury. So that didn't make sense. So they have this dark matter. Now that raises the question of how much matter is there in the universe then, if there's all this other dark matter. And there was also another line of investigation that was turning up at this point on the particle physics level, which I don't need to go into. It is in the book. But it was also saying, oh, there would need to be other matter there as well. But in terms of the community, it was really these beautiful observations of galaxies that convinced a lot of people. So if you have all this matter, and you estimate that 80% of the matter is dark in the universe, you start to say, okay, well, how much matter is there in the universe? And what will the effect be on this kind of eternal question of the fate of the universe? Once you know how much matter is in the universe, and you know at what rate the universe is expanding, you can put those two pieces of information together and find out what the fate of the universe will be. Is there enough matter that the expansion, and this goes back to the Big Bang interpretation of Hubble's observations of galaxies in the 1920s, is the universe expanding like this and slowing down so much that there's so much matter interacting gravitationally that it does this? Or is it doing this and just kind of petering out? So two teams of astronomers using the same kind of methodology looking at supernovae, these exploding stars from far away in the universe, started investigating this and observing. And actually, I'm going to take advantage of this. I don't usually use visual methods, but it occurs to me that in this environment, it might make more sense. If you have what's called a Hubble diagram, if you have velocity versus distance of, distance versus luminosity, you have galaxies that pretty much lie along a straight line. The more distant they are, the less luminous they are, and you can graph it. And Hubble did this in the 1920s, and then other astronomers did this over time. But at some point, this line is going to have to change, because this line holds only if there's no matter in the universe. That something distant the luminosity will fall off at a greater distance and continue along this relationship, this straight line relationship, only if there's no matter in the universe, right? But if there's matter, then gravity is going to have to slow this is going to have to slow the expansion at some point, and the luminosity will fall off because the objects will appear to be closer, right, as it slows down, right? These, rather than a uniform expansion where they would go like this, at some point if they start to slow down, they'll be like this. So they will actually be a little bit, they'll be a little bit brighter, right? They'll fall off like this, okay? So these two teams in the does this make sense? Are you following? Okay, good. So these two teams in the 1990s were trying to figure out, they were using supernovae, using them as standard candles, so-called standard candles, to see at what point would they reach this point where it would start to get, where the supernovae would start to get brighter. And how this curve would determine how much matter there was in the universe. So they were doing this throughout the 1990s, and they didn't like each other, these two teams. And this goes, and I go into some detail in this in the book. It's actually, they were highly competitive. One was primarily a group of physicists from Berkeley, and the other were astronomers, primarily based at Harvard, but also in Chile and Australia. And they, the astronomers didn't like that physicists were getting in on their territory. And the physicists didn't like that the astronomers were coming along after the physicists had been working on the program for 6 years or so, and suddenly, well, from their point of view, suddenly saying, hey, we're going to try this too, and we're astronomers, and we can do it better than you. So there was all this animosity between the two. And this peaked in the 1996, 1997, and there's actually one instance that's in the book, and I don't think it's been reported elsewhere, but at one point, the Berkeley team went to the director of the Space Telescope Institute, which is the Hubble programming headquarters in Baltimore, in the Johns Hopkins campus, and said to him, you know, he went up to him at an astronomy meeting, and he said, you know, we have this method that we're using to find these distant supernovae, and if you use the Hubble Space Telescope, we could really refine the measurements. And the Hubble Space Telescope was supposed to be used only for things that you couldn't do from the ground. And you could do supernovae searches from the ground. But the director said, that's a great idea, that's great science. So he knew members of the other team. So he went to them, the rival team, and he said, Saul Perlmutter up at Berkeley said, Saul has this idea for this program. What do you guys think? And Bob Kirshner at Harvard said, that's a terrible idea. You should only be using Hubble to do observations from for things that you can't do from the ground. And the director said, yeah, but you know, this is really interesting. It's really good science. And Kirshner and his two other astronomers on his team were going, no, 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 we don't want this. This is the wrong approach. You shouldn't let Saul do this. And after a while, as one of the astronomers in the room described to me, he said it kind of dawned on everybody that what the director was saying was, ask for time, I'll give it to you. So when the other team, when the physicists found out that the astronomers were giving each other breaks, they got really upset. In any event, the observations that the two teams made using the Hubble Space Telescope proved to be decisive. And what those observations found was that the universe wasn't doing this. It was doing this, which means that it was that the supernovae were less luminous at a certain distance, that they were in fact farther than they should be, and that implies an accelerating universe rather than a universe that has all this matter in it and all this gravity that's slowing it down. Something was speeding the universe up. Now this is, again, it's a counterintuitive discovery, just like dark matter was, that there's more to galaxies than we can see in any regime of the electromagnetic spectrum. So this is a difficult concept. They tried to knock it down. They couldn't knock it down. And eventually they said, you know, we have results, let's publish. So they published. And the community found it compelling that these two extraordinarily competitive teams who wanted nothing better than to prove the other guys wrong were both reaching the same counterintuitive conclusion. So it was immediately taken seriously. Like within months, people were taking it very seriously. They didn't quite, you know, condone it or believe it yet, but they really felt like, well, maybe there's something here. So this was in 1998. 1999, people are starting to take it seriously. There's, in 2001, one of the astronomers, Adam Rees, on the astronomy team, realized that that you could kind of seal the case. I mean, you can say, okay, it looks like it's speeding up, but what if we don't really know much about supernovae? What if there's gray dust between here and the supernovae? What if, you know, there were all sorts of other factors. Like what if we can't really take these results seriously? And so they thought, well, if the universe is accelerating now at some more distant era out here, and by distant, we're talking about far back in time, right? Because light takes a finite amount of time to reach us. So, okay, so now the universe is speeding up, but at some earlier time when the universe was smaller, matter would have been the primary, would have been primarily under the influence of gravity, and the universe would have been slowing down. So he said, astronomers said, how can we find the point where it might be slowing down? That is, the supernova would begin to become dimmer than we would expect. I'm sorry, brighter than we would expect in this area here. And he realized that there might be in the archives of the Hubble Space Telescope a supernovae from far enough back in the universe that they could make the measurements on it, and there would be follow-up observations by Hubble. Very unlikely, but he knew that there had been 2 supernovae observed in late 1997, and he went into the archives and he thought, you know, this isn't going to happen, but let's see what happens if I run, if I say, did these 2 supernovae in this one particular part of the sky, very, very, very small part of the sky, did they somehow get captured by Hubble, which is looking in every direction, somehow in the following months or years, so months actually, before they faded from view. So he ran the program, and sure enough, it was there because there happened to be a new instrument on board, and they were using it, they were testing it, and they happened to be testing it at exactly that part of the sky. So, I mean, it wasn't exactly, it's like sometimes one of the supernovae was off, was out of the frame, or the other one, or whatever, but there were enough observations that he could actually extract the data from it. And I was at this conference in 2001 where he presented the data, and the other astronomers in the room, there were about 100 of them, already knew what was going to happen because it had been announced at a press conference in Washington the day before. But a lot of things get announced at press conferences and they don't take it seriously until they see the data for themselves. So he walked them through it, and he came up with one of these diagrams again. And this was, he was still using an overhead projector, right? I mean, so it was, and so he's sitting here with his projector, and he's moving something covering it, a sheet of paper, something covering it. So he's moving, so we only see, you know, he's got this part covered. So we see this, well, this part that we already know here, and he shows us some more supernovae that are on the straight line, and then he shows here where it starts to leave the straight line, and then this new supernova was about twice the distance as the others, and so he's doing this. It's kind of like a striptease, and so he moves this one aside, and it's like down here, you know, and the people in the room just gasped, and it convinced a lot of people that they had to take this seriously. Now, where do we come up with the numbers? 73% dark energy, 23% dark matter, 4% the stuff of us. For that, astronomers over the past 10 years have been looking closely at the cosmic microwave background. And you probably have heard of that, and you might know what it is, but just as a reminder, a few 100,000 years after the Big Bang, or what's called the Big Bang, matter and energy went their separate ways. And this is imprinted in the microwave background all around us. And in fact, in the old days, if you were flipping channels on a TV and there was like all that static on channel 3 or channel 6 or whatever, that was about, I don't know, like 5% or something of that was these microwaves from the Big Bang, okay? So people were looking at the Big Bang before they knew what they were looking at. So this cosmic microwave background is imprinted on the sky in microwaves. And it's almost entirely uniform. It was discovered in 1965. It was observed actually in 1964, but the interpretation came out in 1965, that there was this kind of uniform background. But it can't be entirely uniform, or there wouldn't be anything in the universe, and obviously we're here. So there have to be some gradations in there. In the early 1990s, a satellite called the Cosmic Background Explorer, or COBE, observed some of these gradations in just the right amount that it would make sense, that it would match the predictions of the Big Bang. So a lot of people So that really turned the corner for the interpretation of the Big Bang universe. And people really started to, they'd already taken it seriously, but they really started to say, okay, this is valid because now we have this prediction and we have this observation, and the observation matches the prediction, and that's the scientific method. So suddenly cosmology, which used to be metaphysics, was now entering the realm of science. So, and that experiment, the Kobe experiment, won the Nobel Prize in 2006. There was a follow-up called the Wilkinson Microwave Anisotropy Probe, or WMAP, which sent back its first data, I think, in 2003. And then every year or so, they would refine the measurements, the observations, a little bit more. So what they do is they take this really exquisitely precise map of the sky. And you've probably seen it. It has like blue and yellow in it, and it's like an oval shaped, and it's an all-sky map. And these differences are differences in temperature that tell them where the matter and the energy went its separate ways. You can run computer simulations. You can simulate 1 million universes or 10 million universes, and you could say, I'm going to simulate the universe that has 100% matter and no energy in it at all, and that will look one way. And you could say, oh, I'll have a universe that has 63% matter and 47%, rather 37% matter, and that will look different. So they run these millions of simulations. They match it up with the data, the readout from WMAP, and they begin, as they get the data, and it becomes more and more refined over the past decade, it becomes more and more precise, and they are able to say, oh, it matches this universe. It matches this even more precise universe. And the universe that it matches is one that has 73% dark energy, 23% dark matter, and 4% the usual stuff that we think of as the universe. So this is a very compelling argument, and people take it really seriously. And that's where I said at the beginning that people say that this is a genuine revolution. The question still remains, what are these things? We take them seriously. What is dark matter? There were, in the 1970s, the Standard Model was being filled out, but there were still problems in the Standard Model. I should add here that I'm not a scientist, I'm a writer. So there are points where I reach the limits of my understanding, and I'll let you know when they happen. And during the Q&A, I reserve the right to say, I don't know. So, but what I do as a writer is I research this stuff extensively, and I learn it, and because I'm coming from a background of complete ignorance and zero knowledge, I try to figure out like how can I kind of use my process as a way to formulate a narrative for the reader to understand this knowledge in some way that it becomes accessible to people who are non-specialists, people who are even afraid of science, I hope. So when I start getting into the Standard Model, I can't really go very, very deeply, and I had to learn some of it for the book, and I got something entirely wrong, and a physicist was reading an advanced copy, and he got in touch with me, and he said, that paragraph is totally gibberish. And I looked at it, and I said, yeah, you're right. So, but I managed to fix it in time for the book. So the Standard Model had some imperfections in it. And there were two particles that could solve some of the problems, hypothetical particles, right? We don't know if they exist. One is called the axion, and one is called the neutralino. They have properties. If they exist, they would exist in the quantity and at the mass level that if you multiply the quantity times the mass, it would actually make up this 23% dark matter component. Now at the time they didn't know about dark energy, so they were just saying how much of the matter in the universe, and they would say it was 80% of the dark matter was 80% of the matter in the universe. So these two particles seem to be very strong candidates. So they began to set up experiments to find if they could somehow catch these particles. And because these particles, if they exist, would exist by the trillions, and they would be passing, by the trillions per cubic centimeter, and would be passing through you now, as we sit here, they would be plentiful, but we haven't yet figured out a way to capture them in the 1970s. So they worked on this one that I read to you from the prologue, that was the experiment in the underground mine was looking for neutralinos. And they would interact with something and then it would create this detection. And the axion is it's kind of gorgeous, and I'm kind of rooting for it because it's the underdog, you know. But they would take a cavity and with an extraordinarily strong magnet, and they would, you know, get rid of all the light from the cavity, and the axion, if it exists, would interact with magnetism and turn into a photon, which we would be able to see and detect. And that photon would probably trigger a chain reaction and create other photons. But they don't know what the frequency would be, so they have this beautiful experiment. I visited it at Lawrence Livermore. This cylinder, this cavity, that they're looking for this particular signal, but they don't know what the frequency would be, and it's so faint that it's like 10 to the 20 times faint. No, that's not right. No, I'm sorry. It's like 2 or 3 orders of magnitude fainter than the last signal from the Pioneer that left the solar system. So, and at least in that case, NASA knew where the signal was, what the frequency was, but in this case they don't know what the frequency is. So they're looking for this extraordinarily faint signal, and they don't really know where it is. So they just have to kind of methodically go through the radio dial, so to speak, looking for this signal. And it's this kind of, I don't know, quixotic, you know, adventure. But if the axion exists, this experiment will find it. It's just going to exhaust the whole spectrum that it could be at. So, you know, I think that's a lot of fun. So those are the 2 candidates. But starting in the 1970s, when people started looking for them, they said, well, now we have an idea of what we're looking for, and we can build the instruments that will find them. So we'll probably find out what dark matter is in the next 5 years. And people made this prediction, and 5 years would pass, and then they would say it again, and eventually they were saying, well, in the next 10 years, and that passed. And the most recent one I saw was, well, there were 2. One was in 2001. I mentioned Vera Rubin, this discoverer of the flat rotation curves in the 1970s. I was at a conference, and she said, everybody keeps saying it's going to be found in the next 10 years. I said that in 1980. I think we have to stop saying this. And then I saw her over the weekend in Washington, and she said, you know, in 2005, I was at another conference. People got upset with me because they were standing up and saying, we're going to find it in the next 5 years. And I said, people have been saying this for 25 years. You have to stop saying this. And they said, no, this time it's true. Of course, now it's 2011, so it's been 6 years since that last prediction. So this is really perturbing them. Okay, so that's on the dark matter side. On the dark energy side, it's not so much a matter of what is it. At this point, it's just a matter of figuring out how it behaves. So the experiments that they're designing now, that they've been running for the past few years, are trying to figure out, this dark energy, this whatever it is, this component of the universe that is overwhelming gravity on a cosmic scale and causing the acceleration to speed up, is it constant over space and time, or does it change over space and time? So they don't even know. I mean, it's not a matter of, well, what is it exactly? They're just trying to figure out, like, on this kind of cosmic scale, how does it behave before they can even begin to figure out the other issues. Complicating dark energy is that, according to quantum mechanics, there's no such thing as empty space, right? That antiparticles, or virtual particles are popping into and out of existence. As one of the discoverers of dark energy told me, he said, you know, there's this circuit. It's like we're sitting here reading a newspaper and there's a circus going on around us, and we just can't see the world on the quantum level. But according to quantum theory, if this kind of vacuum energy, if this energy exists, it should exist at 10 to the 120 times more powerful than what it would be in our universe. I mean, at 10 to the 120 times, the universe wouldn't exist. I mean, it would just be, you know, it would have obliterated in the first fraction of a second. So we know it's not 10 to the 120, and we know it's not 0 because we're making this observation. We know that it's like really, really small. And why should it be so small? Why should there be this 10 to the 120, or if you do other calculations, 10 to the 60, or if you do other calculations, 10 to infinity? Why should there be that kind of discrepancy between observation and theory? The problem is that we can't reconcile general theory of relativity with quantum theory. The general theory of relativity, of course, describes the universe on this grand scale where we can see the interactions of these big things, galaxies, and we can predict the motions of planets. Quantum theory, of course, exists on the very small level, and they can't get the two to match, as I'm sure you're aware. Einstein worked on the problem, other people worked on the problem, but it's dark energy that has really brought that problem to the forefront in a way that science has had to say, okay, now we really have to take this seriously. We've been able to live with this discrepancy for the last 70 years or so, figuring that at some point somebody would come along and figure it out. But now, it's not only that sometimes somebody will come along and figure it out, but somebody has to come along and figure it out, because otherwise this part of the universe, the 73%, is totally unknown and seems to contradict all the laws of physics as we know them. So this is part of why they're saying that this is a revolutionary moment, because we're going to need to reconcile these two in order to figure out what the universe is. Will that happen? Maybe not within our lifetimes, maybe never. And this, again, is kind of the dark matter problem, where they've been running these experiments for 30 years now and haven't been able to find these two candidate particles. What if they don't find the particles? What if they need detectors, or if they need accelerators that are beyond the scope that we can build or we can afford to build? So this is a problem in that community, in the particle physics community, wondering whether or not, even if the particles are out there, will we ever be able to get to them? Same thing with dark energy. How are we going to be able to reconcile these two grand theories? Each one makes sense, it makes predictions, it's totally consistent within itself, but they're inconsistent with each other. So that's the point that astronomy, cosmology, and physics is at today. They don't know whether or not they're going to be able to solve these problems. They feel very strongly that these two components of the universe, the dark matter and the dark energy, exist, but they don't know what they are, or how, or whether or not they're even going to be able to find them. And this obviously can have very profound implications for physics, as I said, and for philosophy in some way. In the same way, I think that, as I said at the beginning, Galileos Revolution had these repercussions. You know, when Galileo was observing the moons of Jupiter, you would have been hard-pressed to say, well, in 150 years we're going to have the Enlightenment and then democracies, and there will be revolutions based on the idea that the individual is in control of information, not the church, not the king, but that the individual can make these observations, and then somebody else with the same instrument, you hand off the telescope, can make the same observation. And then Newton comes along and comes up with, and works with Kepler's ideas and creates this new physics, where the universe runs like, in the cliche, runs like clockwork, and then Einstein comes along and modifies it. This, if I'm correct, and if the scientists who are working on this are correct, as I said at the beginning, it's like we're in 1610 all over again. There's this revolution going on. We have every reason to believe that these observations are valid, and we don't know what the outcome is going to be. We don't know what effects are going to be. What I want to do with this book, and in showing how these people, these rivalries, and how these people who were racing each other throughout the 1990s to make an observation, made the observation. They succeeded, but they opened up this whole other realm of what we don't know in the universe. And I also want to say that the scientists find this invigorating. They don't sit there and go, oh, what have we done? We don't know the answer. The fact that they don't know the answer, the fact that they came up with a result, and then that opened up a bigger mystery, is very exciting. And I quote this in the book. There was a theorist at a conference I went to, and he said, if you could put the whole timeline of the history of science in front of me, this is where I'd want to be. And this is a sentiment I hear again and again and again in the community, that people are really excited by this. They're frustrated, but they're also really excited because they know that this is something that is going to have these profound implications for centuries to come. We just don't know what those implications are. So part of the purpose, as I said at the beginning of my writing this book, is to just let people know, people like yourselves who have heard about dark matter and dark energy and probably have some knowledge of it, put it into this broad historical context so that we can begin to see that this revolution is taking place. And yeah, we don't know what it means, but we know that it's important. So I'll stop there and I'll ask for questions, if anybody has them, and if I have any answers. Let's see. Yes?
I have very little technical knowledge in this area, but maybe I'll interpret this. It would seem to me that there have to be a huge number of assumptions behind these the interpretations of the data, like the thing about a galaxy like ours should have under normal conditions split apart. The fact that it didn't is evidence that there's something else going on. How sound are all the assumptions that suggest that there's an anomaly?
Yeah, good question. Obviously, scientists ask themselves the same question: how sound are our assumptions? The analogy you could use is that, well, there's an effect here, right? And they're inferring from the effect, but it's similar to gravity. We don't know what gravity is, but we know we can come up with the equations that match our observations, but we still don't know what gravity is. I mean, that's part of the whole general relativity quantum problem, that we can't reconcile the two, and where a lot of it breaks down is in the realm of gravity. And I'm actually hoping that my next book will be on that subject, and even my editor doesn't know that, but I'm talking with her next week. So it's difficult to say, and it's slightly beyond my area of expertise, except that people are used to thinking in this way and saying, we know that there's an effect there, and we have to make an inference based on that effect. Now, it's always possible that Newton was wrong and Einstein's modifications of Newton were wrong, and that all we need to do is modify gravity, and people are working on that. And Vera Rubin, this astronomer I mentioned, the flat line galactic rotation astronomer, I saw her over the weekend as well in Washington. And she's 82, and she made these extraordinary discoveries, and they changed the astronomy and they changed cosmology. But she's still sitting there saying, "Look, we haven't found the dark matter. Maybe it is modified gravity. I don't know." But the observations of the cosmic microwave background that I mentioned at the beginning so closely match, the computer simulations, the simulations of the universe, that people are pretty confident that the inferences that they've made, that you're talking about, and the assumptions were valid and got us this far. But could things be wrong? Things are often wrong in science. So, can't say it with certainty, but with a high level of confidence, I think. Thanks. Yes?
Are there any assumptions about the nature of dark energy that distinguish it from the four basic forces?
I'm not sure exactly what you mean, but because it's...
Nuclear
force,
gravity, magnetism, and so on.
I'm not hearing that. I'm not hearing that in the community. I'm not hearing the need for another force. They're more working with, on the theoretical level, they're willing to try anything. I mean, the observers are very frustrated because I saw this one observer, one of the discoverers of dark energy, the leader of the astronomer team at a conference, at a room full of theorists. He said, "Give us something to work with. We're dying to go out and make these observations, but you guys are not coming up with theories that we can go out and test." And some of these theories are that there's a parallel universe and it's intersecting with ours, and we perceive gravity as the artifact of this intersection of the two universes. But I don't hear, so in that sense, there's questioning of the four forces, that why is gravity so weak compared to the other three forces? But I'm not hearing an invocation of a fifth force, if that answers your question. Okay. Yeah. Yes?
In your
conversations, what are the experiments that are being set up right now that physicists are excited about for results in the next 10 years that we should keep in the background?
Okay. There are several methods that have been developed in the last 10 years beyond the supernovae that I've been talking about. For dark energy, are you talking about? Or for dark matter? Okay. Well, the dark matter experiment, this one that I mentioned, is I think it's in phase 2 or phase 3 now. I'm not sure, but it's getting to the point where it will supposedly have a result within the next decade. Large Hadron Collider, it's a telescope of a different sort in that it recreates conditions in the first moments of the universe, and it's possible that it will spit out one of these candidate particles for dark matter. On the dark energy side, as I started to say, there are these different methods. One is using gravitational lensing, which is where you put a galaxy in front of another galaxy, and you can see the galaxy behind because the light is distorted, and you can recreate the galaxy. You can also use it to find out how much mass the foreground galaxy has, and then you can compare it with observations and say, this is the mass we see, and this is the mass that must be there. And again, it's that dark matter issue. But you can also use that to map galaxies and how galaxies are mapped over time as we go back farther and farther away in the universe, how the large-scale structure of how galaxies, in this kind of lattice. I don't know if you've ever seen these recreations of the universe on very large scale through observations like the Sloan Digital Survey, where there are these, where it kind of looks like a cobweb, so that it's all filamentary, so that there are great gaps between the clusters that are strung around, and then there are these kind of these kind of centers where everything is kind of tightly packed. So those observations, as you look back in this kind of way, where this is us, and then you look farther and farther back at this stretch of the sky, and as you're looking farther out, you're looking farther back in time, and you can see how the large-scale structures changed over time. That will tell you how dark energy, how the expansion changed the structure and evolution of the universe over time. So those are going on. The South Pole Telescope, which I went to visit, which is right at the South Pole, which is very cool, is looking at galaxy clusters using something called the Sunyaev-Zeldovich effect, which I don't need to go into, but it uses the cosmic microwave background, uses photons from the cosmic microwave background, how they've changed in their journey from there to us by intervening galaxies to map these clusters using a different methodology so that they can compare the two methodologies. Dark energy, there's a decadal survey that the National Research Council publishes every 10 years, and last year dark energy was made the highest priority both in space and on the ground. But the telescope, which has been on and off the drawing board for 10 years, is in tons of trouble because the James Webb Space Telescope, which should have launched a couple of years ago and is billions of dollars over budget, is still several years away from launching and is still $1.6 billion short of where it needs to be, is gobbling up all the resources, and they can't begin that until James Webb launches, which is now the middle of the decade, which means that telescope wouldn't be online until the middle of the 2020s. So there's a lot of frustration in the community about that. So those are the big ones that you can keep an eye on. Yes?
Sorry if I missed that from your speech. Is there a relationship between antimatter and the dark matter?
This question came up. This is beyond what I know. But this question came up over the weekend, and at this talk I was giving, where there was a dark matter and a dark energy people present, and I'm not sure, but I seem to remember that the answer was no. But I can't say that with certainty, and I'm sorry.
Is the antimatter part of those 4%?
I'm just. This is now. This is the part where I get to say, I don't know. and beg your indulgence. Thanks. Yes.
So as a writer versus being a scientist, you're obviously talking to a lot of different scientists, some of which will come down more philosophically, maybe on one side and think that there's this anthropic principle about
Right.
how everything is finely tuned, and then there's people who are maybe looking at string theory and thinking it's the be all and end all and stuff. From the people that you've spoken to, do you have you been able to maintain pure objectivity, or are you finding yourself going more in one direction or another?
Well, in terms of the interpretation of what they're saying, I try to. There is no such thing as pure objectivity. So I mean, I concede that right away. I mean, every time I tell my writing students this, that every time you begin to write, no matter what it is, you're choosing, even if it's the at the beginning of a sentence, you're choosing from millions of choices, and you're making one choice, and it's a subjective choice. In terms of the anthropic principle, I have two ways to answer that question. One, if you don't know what the anthropic principle is, it's like, why is the universe so finely tuned to life for us to be here, that we can actually observe it, that there is this 73%, 23%, 4% ratio that allows for the universe to survive long enough for us to be here. It's such an improbable, unlikely collection of physics that, why would it be there? Personally, I like the anthropic principle a lot, because what it says basically is that this idea of more is continuing, that Galileo goes out and sees more planets, more stars, etc. Hubble sees more galaxies. We continue to see galaxies. Now we see that there are that there is matter and energy that we can't interact with through our five senses in the way that we've normally been able to do astronomy. So I don't see any problem with there being other universes. In which case, and in fact, according to quantum theory, there should be other universes. If our universe comes out of a quantum fluctuation, this idea that space isn't empty, that there's always these virtual particles popping into existence, and that would be the origin of what we think of as our universe, this kind of quantum pop. And in fact, that would lead to this period of inflation, which you might have heard about, which is that in the first fraction of a second, the universe inflated at an extraordinary rate. If that happened once, theorists can't find a way to turn that off. So there should be infinite inflation. I mean, it should just be going and going and going, so that all these other universes are popping into existence. And if they run the numbers, maybe infinite is a little strong, but there should be 10 to the 500 universes. And if there are 10 to the 500 universes, then ours just happens to be the one that has this collection of physics that allows us to be here and ask the question. That's the anthropic principle. People take inflation very, very seriously, and it's part of the model now. It's part of the standard cosmological model. I said earlier that cosmology has gone from metaphysics to physics in the last quarter of a century, 30 years, 40, 50 years. Inflation is now part of it, so that they say it's the lambda, which refers to dark energy, lambda, cold, dark matter plus inflation model. So does that answer your question? Okay, yeah.
You had a particular.
Yeah. Well, and as I mentioned WMAP, and I saw people at the beginning of the decade like virulently anti-anthropic, and because of WMAP, because WMAP seems to be impossible to have, as far as we know, without inflation. And once you have inflation, you have this, all these other universes popping into existence. I'm seeing that people are now going over to the anthropic side and kind of saying we have to take it more seriously, and we have to figure out can it make an observable prediction. And that's the challenge now, is how to take this idea and make it into science. Is there a question back there somewhere? I thought I saw a hand. No?
Just
Yeah.
what you were saying.
Last question,
Okay.
if that's okay.
If there are 10 to the power 500 other universes, who's to say there's not somebody else sitting out there wondering what all the dark matter in the universe is for? I mean, that doesn't make this universe unique.
So you're saying another universe would have dark matter as well?
No, there could be some other humans sitting in some other universe and looking at their universe and saying, oh, this is so great, they just created this just for us.
Right. Yeah. Exactly. I mean, it raises all these kind of profound questions, I think. And there are people who will argue that there has to be another universe that is identical to ours, so that there's somebody else asking that question right now.
Great.
So that, I guess we're out of time, so thank you very much. I appreciate it.